So chapter 4 introduces us to two-dimensional motion. We start off by imagining that we have a position vector. We can call it position vector r, and it's got some magnitude. So the magnitude of r is, we can call that r, it's at some angle theta. And so it's got an x part and a y part. So the x part here is going to be equal to r cosine theta, and the y part is going to be equal to r sine theta. Now, in principle, it can even have a z component too. So we're going to start with two-dimensional motion and then expand this to 3 dimensions. And so we would say that vector r could be equal to r cosine theta I plus r sine theta j. Now we'll get back to this later in terms of describing this, but r is our position vector. V is going to be equal to dr dt. Okay, and so obviously if it doesn't, what can change is it could change in length or it could change in angle. So either one of these could change. And so that would determine this. Now again, that's getting a little further ahead of where we're at, but that's the next step. And then the next step after that would be the acceleration is dv dt. All right, so let's start off though with just a vector here, r. Okay, so an r vector, and we're going to say it has an x part in the I direction and a y part in the j direction and a z part in the k direction. So v vector is dr dt. Well, dx dt is just going to be the x velocity. dy dt is just going to be the y velocity. dz dt is just going to be the z velocity. Okay. Now talk about acceleration. That's going to be dv dt. So the derivative of Vx is just going to be Ax. The derivative of Vy is Ay. And the derivative of Vz is going to be Az. Now notice that this is to this is to that. That's the same as we normally have had. This is to that with exactly the same relationship, and same here. So for all the x parts, then we can say, just like before, x equals x naught plus v naught t plus 1/2 at squared, assuming constant acceleration. And we're going to assume a constant acceleration vector. Okay, so, but the derivative of that, we're going to make this the x's here. So those are all x components. So that's exactly the same as we had before. Well, because the y relationships are the same way, then that means that the mathematics comes out the same. So that's going to also be the same. And then the z components, same thing. So before we had 2 equations, now we have 6 equations. You know, because now we can handle the motion with constant acceleration in all 3 directions. And so that's going to be the basics of 2 or 3-dimensional motion. Is we just got to keep track of all of these things. And so that's how we're going to start all this. So this is the principal derivation of it. Again, we assumed constant acceleration here, okay, because we kind of ended our discussion of one-dimensional motion with constant acceleration, and we did some examples. So we're going to start our two-dimensional motion off of constant acceleration. Now we're going to change this and make it a little more complicated in just a little bit, but this is how we're going to start everything.